All right, so today we are going to learn about Maxwell's law of induction. But before that, let me remind you of Faraday's law of electromagnetic induction. Recall that Faraday's law said that if there is a change in the magnetic flux, then there is an induced electric field. And what we learned is that the induced electric field that forms closed loops, the E dot ds, will be equal to negative of d phi b over dt. That means the rate of change of magnetic flux. Now, Maxwell said that if changing magnetic flux produces an induced electric field, then shouldn't induced magnetic field be produced by changing electric flux? So in other words, he said changing electric flux should produce magnetic field. And it turns out that Maxwell's idea was correct. And so this symmetry argument can actually be shown to be correct, and the law that actually summarizes it is called Maxwell's law of induction. And it says that the induced magnetic field in B induced dot ds through a closed loop is equal to mu 0 epsilon 0 d phi of E over dt, where phi of E is the electric flux. So it's integral E dot dA. And so you can see that Maxwell's law of induction basically says that if the rate of change of electric flux here is related to the integral over a closed loop of B induced and dot ds. Notice that these two laws, Faraday's law and Maxwell's law, are very similar, just that there is no minus sign here, unlike the Faraday's law. Also, let me remind you that induced magnetic field is produced due to changing electric flux, and flux is defined as integral E dot dA. Now, if the electric field magnitude is constant, and makes the same angle at all points on the entire area that you're integrating over, then you can pull the electric field out of the integral, and you can say that phi of E, the electric flux, is just E dot integral dA, which will turn out to give you the total area A. And this is basically equal to magnitude of E, magnitude of A, times cosine of the angle theta between the electric field and the area vector. Now, if electric field and area vector point in the same direction, so in that case, so if E vector is parallel to the area, in that case, theta is going to be 0 degrees, and in that case, cosine 0 degrees is going to be 1, and the electric flux can be written as just magnitude of E times magnitude of A. Now, one situation in which Maxwell's law of induction can be tested is when we are charging a capacitor, because in that case, the electric flux is changing with time, and so there is a d phi of E over dt. Another case would be when we are discharging a capacitor, and in that case also you have a d phi of E over dt. So now notice something very interesting. This Maxwell's law of induction should remind you of Amperes law. So let me remind you about Amperes law. And Amperes law stated that integral B dot ds over any closed loop was equal to mu 0 times the current that is enclosed. So notice that Ampere's law is not talking about changing electric flux inducing a magnetic field, but it's talking about current producing magnetic field. But it's very similar to Maxwell's law of induction, and if you compare the left-hand side, the dimensions are exactly the same, so the right-hand side should have the same dimensions, and hence I enclosed here should have the same dimensions as the dimensions of epsilon 0 d phi e over dt. And in other words, epsilon 0 d phi e over dt should correspond to some kind of fictitious current. And that fictitious current is actually called displacement current. So we can say ID enclosed is equal to epsilon 0 d phi of E over dt, and using that we can say that Maxwell's law of induction can be written as integral B induced dot ds, and this is the induced magnetic field due to changing electric flux that is equal to mu 0 times ID enclosed. This puts it in a form which is very similar to Ampere's law. So this is basically Maxwell's law of induction. Notice that this ID enclosed obviously is nothing, so ID enclosed is epsilon 0 d phi of E over dt. So this is a fictitious current which is related to the changing electric flux with time. Now the question is, how should this ID relate to the current that might be flowing in the wire? For example, let's consider the case where we are actually charging a capacitor. Because in that case, we do know that there is a changing electric flux. So let's consider the case where we have simple situation. You have parallel plate capacitor. These are the two plates, and we connect it into a circuit. Here is my battery with the positive and the negative, and here is a switch, and here is the complete circuit. Now as soon as I close the switch here, basically the electrons will start flowing in the counterclockwise direction. In other words, electrons will start accumulating here, positive charges here, electrons, more and more electrons and positive charges accumulate, and you can see that there will be a charge plus Q here at any given time and minus Q here, and there is an electric field that is building between the two plates, like this. And so there is a current that is flowing in this wire here, and the current is obviously flowing from positive to negative, so we can say that there is a conduction current, I sub C, that is flowing in the wire. And let's try to relate how this I sub C relates to the displacement current I sub T. So in order to do that, let's think about the electric field between the two plates E at any given time. These arrows are showing you the direction of the electric field, which is from the positive plate of the capacitor to the negative plate, and this electric field is increasing with time. Notice that the area here that we are talking about is the area of the plates here. Let's say that the area of each plate is A, and the area vector is obviously perpendicular to the area. So in this case, the electric field and the area vector, they both point in the same direction. And so when we are talking about the electric flux phi of E, that's an electric field is also constant at any given time. It's just going to have the magnitude E times A, because cosine of the angle between the two is 0. So cosine 0 is 1, and so this is just nothing but E times A. Okay? Now, also remember that the electric field between the two plates of a parallel plate capacitor had the magnitude sigma over epsilon 0. And sigma was nothing but Q divided by the area of the plate. So basically from here we can see that Q can be written as E A epsilon 0. So if I look at how the charge is changing with time, as the electric field is changing with time, I can say dq over dt is equal to d over dt of E A epsilon 0. But the only thing that's changing here is the electric field. And by the way, this dq over dt is nothing but this conduction current here that's flowing in the wire. So I can call that I sub c, and that's equal to, I can pull out epsilon 0 and A, if you like, and then it's dE over dt. But, or I can actually keep the A inside, and I can say that I sub c is equal to epsilon 0 d over dt of E times A. And this is the electric flux. So IC is equal to epsilon 0 d phi sub E over dt. But this is what we call the displacement current. So what we are seeing is that the conduction current and displacement current are equal actually. So it's as though when you're charging the capacitor, you have a displacement current that is equal to the conduction current that is flowing in the wire, and the displacement current is actually flowing between the plates of the two capacitors. Of course, displacement current is a fictitious current. So it's really epsilon 0 d phi E over dt, but it has the unit of real current. So here is your switch. As soon as you close the switch, what you see is that there is a real current in this wire, I sub c. This is the conduction current. And in addition to this, there is also you can think that there is a fictitious current between the two plates of the capacitor, I sub d, and this I sub d should be thought of as flowing through this fat pipe, between the whole capacitor. So, but I sub c and I sub d basically complement each other, as though this circuit is completed when you actually think of a current flowing through the between the plates of the capacitor as the capacitor is charging and more charges are accumulating between the two plates. So notice that this displacement current will only be there for the period of time when the electric flux is changing, because I sub d will be equal to epsilon 0 d phi sub E over dt. So the electric flux has to be changing with time, and the rate of change of that will actually determine what the displacement current is. In this case, notice when we are charging the capacitor, the electric field is also pointing from the positive plate to the negative plate, and the displacement current is in the same direction. Now let's think about what happens when we are discharging a capacitor. Because when we are discharging a capacitor, in that case, we basically have no battery in the circuit. So we have a charged capacitor. Let's say this is positive with some charge Q, and this is minus Q, equal amount of charge but opposite sign, and the electric field is still pointing like this from the positive to the negative. And this time, when we actually connect this in a circuit and close the switch here, what will happen? Well, this time the electrons will go from the negative through the wire and they'll go towards the positive, and so we can say that a conduction current is flowing in the direction opposite to the direction in which the current was flowing during charging. So the conduction current is flowing like this time in the counterclockwise direction, and so the displacement current can again be thought of as a fictitious current that's flowing between the plates of the capacitor, and this time the displacement current will be flowing opposite to the direction of electric field. So that's going to be the direction of I sub d, and it can be thought of as flowing between the two plates of the capacitor in that region. And again, I sub c will be equal to I sub d even in this case. But notice that in this case, the displacement current is opposite to the direction of the electric field between the two plates when we are discharging a capacitor. And again, the displacement current will be flowing when the electric flux is changing with time. So again, the total displacement current between the whole plate will be epsilon 0 d phi sub E over dt.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.